Right, okay, CISC versus RISC. So we've got CISC and RISC. Two strategy approaches to getting the instruction sets. Hang on. Right, Commodore 64, what did you say before?
Correct, so CISC, complex instruction set computing, has a larger variety of different instructions that it can decode and execute.
So it has a large instruction set.
Yeah.
I'm using a very fat pen here. Right, so it's a large, that's better. Large instruction set, right. So the consequence of that is what?
There are more instructions it can do in one fetch decode there are like more things it can do in one instruction, but sometimes it needs multiple fetch decode executes to do one instruction.
You've got to be careful. Right. So we have complex instructions that can do multiple jobs.
Yeah.
But they can take several clock cycles.
Oh yeah, that was it.
It's not fetch decode. Fetch decode is fetching an instruction.
Yeah.
So, but they take, and it's a varying number.
Yeah, I had cycles in my head, so I sort of
numbers of cycles. So this could be down, so as little as 4, so the quickest instruction, so you might have 4 cycles for the quick instructions, all the way up to, and it can be worse than this, but it can be up to like 70 cycles. So on a Motorola 68000, you can do not, add in 4 cycles, but if you do a division instruction, it's 70. If you do it signed, unsigned's quicker. Okay, so you've got this. So it's difficult. So as a compiler, it's difficult to estimate how long everything's going to take because it depends on what instructions you use. But it does mean, because you've got these complex instructions, you can implement high-level language features in single instructions. So you can, so it takes fewer instructions to implement high-level language. So this is what the compiler has to do. So high-level language features. Such as loops. So for instance, in Z80, there is an instruction, LDIR, which copies from one location in memory, pointed to a register, to another location, increments the 2 registers, so you copy from one array to another, and decrements the counter, and it keeps doing that until the counter gets to 0, but it only takes one instruction. If you used to write that manually, you'd have to use multiple instructions, so it actually takes a little space up. So that's the benefit of the fewer instructions. So they will be smaller programs. So generally, will allow you to create more compact, smaller programs. So that's a general. With varying execution times for the elements. Because they're packaged up. Now the massive knock-on of this, not only have you got this like difference in execution time, because you've got more instructions, the decode takes longer. Because you've got big old dictionaries, so the decode takes longer or is more complex. Because you've got more to decode. And part of it, that's where the complexity thing comes from. Because you've got different lengths of instruction format. Okay, so we've got different lengths. So all these things are what make, and this was the approach Intel took, and have now got stuck with. So different length instructions. And that's why it's harder to decode, because you know, we've looked at instructions. When we did the addressing modes, there were instructions where we kept fetching stuff. Okay. Right, okay, so the RISC then, so yeah, it stands for reduced. So we've got a simpler instruction format, usually fixed, so it might be a 64-bit or a 32-bit format, and that is it. Okay, so simpler instruction format generally have a hell of a lot more registers as well. Lots of like general registers and address registers. See, some RISC machines have got like 64 registers. So you can actually keep a lot of data on the CPU. You don't even have to go back to cache if you can write your programs in a certain way. And the golden goal of RISC is to do one instruction per cycle. So they're blindingly fast. So what you do is you dedicate more silicon to implementing features so that they are execute fast. And that also includes complicated tasks as well. That's what GPUs do. But they've only got like, 60 instructions on a GPU, but they can do them in one cycle. Okay, yeah, so you got that, but the knock-on of that, as you said earlier, was in order to implement code, the compiler has to put lots of instructions together. So you generally need more instructions to implement high-level language features. But the decode's simple. Now, because these are so fast, what effects does that have on the operation of the CPU? So in terms of like how fast you run the CPUs, how much power they use. So what's the general rule of thumb with CISC and RISC?
If I remember it correctly, I think CISC required more power, and it generated more heat as well, I think.
Yeah, so CISC is power hungry. And as soon as you do, can I spell hungry? Is it that?
It's the G, I think.
That is the G.
No, sorry.
Is that right?
Yeah. Sorry.
Right. So CISC is power. As soon as you start sucking power, then you're going to have increased heat. If you've got increased heat, you have to increase cooling. It's a bit like the episode of Futurama when Fry's on the Mars and he puts the heater on because it's cold, and then he puts the air conditioner on because it's too hot, and then run out of battery really quick because he's an idiot. Yeah, so you need to increase the cooling, which increases the amount of power you use, etc., etc. Okay, you tend to also run them at very high frequencies. So you run them at high clocks. You need desktop power supplies to be able to do that. So they're a desktop device, aren't they? As the original laptops can prove with their 30-minute battery life. Awful things. You had to have them plugged in. They were just portable computers, really. Right, so with the RISC, you've got lower clocks. And because you're running at lower clocks, less power. In fact, so little power that they can run off battery for very extended amounts of time. Because they're running at lower clocks and they're using less power, less heat. So you can do passive cooling. So you don't need fans. So they're actually good for low noise environments and applications. So that's a big trade-off. So they're really suitable for portable devices. They're just more efficient. I can't spell. I don't know what's going on with my brain at the minute. Yeah, so they're more suitable for portable devices. It's a completely different strategy. You know, you're just saying like, I want to be very good at doing a few things rather than having this incredibly massive instruction set that what you actually find that the compiler doesn't use half the instructions anyway. So you're dedicating silicon to instructions that are hardly ever used. Apart from that weirdo programmer who needs to use that specific instruction. And the other thing is, the reason Intel is stuck with CISC is because of all that legacy stuff. There's a reason it's still called x64 and it's got the X, because it runs x86 hardware modes. It's crazy, absolutely mad.
So what does that say? Lower what?
Clocks.
Oh, clock.
Yeah, it's not very good, is it? Let's just write it in another colour just to help you. Fat pen. I must have been doing something that needed a fat pen. Okay. Yeah, so one thing you'll get asked about is, it'll be, requires fewer, there was a really stupid question that the exam board messed up and got the wrong way around. They said the difference between CISC and RISC, so CISC, so they'll always compare them, so all these features, CISC versus RISC, so you'd say it's less instructions, more instructions to do the same task. You'd say higher clock, lower clock, and it's, remember the key is not just stating these things, it's the consequence of that. So even when you throttle down a mobile processor that's a RISC processor, which all the ARM designs are, when you lower them down, they're still executing instructions really quick, even if so you don't need to get through the instructions, you don't need that clock speeds. And you get to breakdown points anyway with clock speeds. Once you start getting above 5 gigahertz, it starts to all go horribly wrong. And the heat generated is massive and everything starts to thermally break down. Okay, so you'll get asked about those things in relation to high-level languages and low-level languages. Okay, right, stop that one there.